All right, good morning, students. Okay, so today, as usual, we are going to just recap first on what we have learned in the previous lesson. Okay, so previously it's really 1.3. Since I started the recording from 1.0, it means that we have gone through 4 lectures already. Okay, so previously in the previous lecture, we learned about concentration. So we learned that there are 2 types of concentration, one in the term of mass over volume, another one in the term of number of mole over volume. Okay, mass over volume, so what unit will you get? Okay, gram per decimeter cube, gram per liter, gram per centimeter cube, as long as it's the volume. Okay, what about number of mole per volume? What is the unit that we will get? Okay, mole per decimeter cube. So this is also known as what? Molarity. Okay, so this whole thing, number of mole over volume, is a concentration. This concentration is also known as molarity. Okay, be careful, the floor is very wet. Okay, so next, we learn to solve stoichiometry involving molarity. Okay, so stoichiometry, again, it means a chemical equation. So I have this chemical equation, and then remember we solve questions like if I have molarity of this, volume of this, molarity of this, calculate what is the volume. Okay, things like that. So this is what it meant by solving stoichiometry involving molarity. Okay, so we've done this as well. Okay, next, we move on to Avogadro's law. So what do you remember about Avogadro's law? Anything? Directly proportional. What is directly proportional? Which one is directly proportional to what? Okay, volume directly proportional to number of mole. So directly proportional means if the volume increase, number of mole also increase. So this is Avogadro's law. Okay, and lastly, we learned 2 new conditions. Okay, we have STP and RTP. Okay, what is STP? What is RTP? Standard. Okay, this is standard temperature and pressure, and RTP is room temperature and pressure. Okay, what is the room temperature and pressure? 25 degrees Celsius, 1 atm. 1 atmosphere, okay, 1 atm. Atm is the unit for pressure. Okay, what about standard temperature? Very good, 0 degrees Celsius, 1 atm. Okay, what does this STP and RTP say? Okay, STP, what does it say? 1 mole of any gases, 22.4 decimeter cube. Okay, 1 mole of any gases, if the gas is at STP, under this standard temperature and pressure, that 1 mole of gas will always occupy 22.4 volume. Okay, 22.4 decimeter cube of volume. Okay, what about RTP? 1 mole will always occupy 24. Okay, 1 mole of any gases at room temperature and pressure will always occupy 24 decimeter cube. All right? Okay, anything you want to clarify? Any questions? Good. Okay, let's proceed to today's lecture. Okay, so this week I want to give you another quote. Okay, so this quote is it's not about you being perfect. Okay, it's about the small effort that you make. So last weekend and these few days, I received a lot of messages from you guys. A lot of you are trying to watch back the recording, trying to do revision, asking questions. Okay, asking how can you improve and things like that. Okay, of course I don't expect all my students to score A and 100%. If they do, that's a blessing, okay? But at least if, let's say, you know you are weak, you are trying, okay? Every day you try a little bit, a little bit, a little bit. The effort, okay, is what it matters, okay? Don't feel very down just because you cannot score 100%, okay? You don't need to be perfect, okay? It's all the small things. That's how change occurs. Okay, so we are in the last part of chapter 1. Okay, I would like to remind you this is still chapter 1. It means that this will still goes into your quiz 1 next week. Okay, but this is the last part. Okay, previously, okay, as usual, learning outcomes, I will highlight at the end of each lecture, so I'm not going to go through this. Okay, so states of matter. Everything around us is made of matter. Okay, there are 3 types of matter. What are they? Solid, liquid, and gas. Okay, remember how I recapped previously? I said we talked about solid, mass over molar mass. Okay, we talked about liquid last week. Okay, molarity. What is solution? What is solvent? What is solute? Okay, so today we are going to move the whole lecture into gases. Okay, so solid, it has a fixed shape. Okay, you have so many types of shapes around you when it is solid. Okay, liquid, it takes the shape of the container. Okay, let's say if you buy a special water bottle, which is Hello Kitty in shape, then your water will take the shape of the container. All right. Okay, and then gases also will not have fixed shape. If you blow your carbon dioxide into an A-shaped balloon, okay, happy birthday, HAPPY. So your A, your carbon dioxide will take up the shape of the balloon, okay, also no fixed shape. And gases have no fixed volume because even after you blow it, you can compress it. When you compress it, it becomes small. Okay, when you don't compress it, it is large volume. Okay, so gases. Remember previous lesson, I mentioned there are 4 factors which are important when we talk about gases. Okay, do you remember what are the 4 factors? We have pressure, we have volume, we have temperature, and molar amount. Molar amount means number of mole. Okay, so when we talk about gases and later we talk about gas laws, we will be talking about all these 4 factors. Pressure, volume, temperature, and number of mole. Okay, and then we are going to relate them in multiple formulas. Okay, next, today we are also going to learn the last part, kinetic molecular theory. Okay, so as the name suggests, kinetic. What do you understand about this word kinetic? Okay, moving, movement, what else? Energy. Okay, so we will talk about the movement of the gas molecules. Okay, the theory about the movement of the gas molecules. That is kinetic molecular theory. Okay, so the theory will explain, okay, what is the relationship between pressure, volume, temperature, and number of mole, the 4 factors. Okay, so of course, before we go further, we have to understand the unit. We have talked about the unit of number of mole. We have talked about the unit of volume. It can be decimeter cube, liter, the conversion centimeter cube. So now we talk about unit of pressure. Okay, so commonly that you are going to see in chemistry 1, okay, the pressure that we will use will be in the unit of Pascal, PA, or atmosphere, ATM. Okay, you know, STP is 1 ATM, RTP is 1 ATM. Okay, may I ask you, around you, what is the pressure of the gases around you? How much? Why 1 ATM? Because it is atmospheric, it's room temperature and pressure. Okay, so it's 1 ATM. That's how you relate what you learn with what you have. Okay, all right, so even though IUPAC, okay, recommended to use the unit bar, but in chemistry, we still use ATM or Pascal or kilopascal. Okay, we are going to do some calculations later. Okay, before we go into calculation, let's try to just do conversions of unit. Oh, before that, one thing I forgot. Anybody came across this? MMHG, what is it? Millimeter. Millimeter? Okay, millimeter mercury. Okay, you know that Hg is mercury. All right, but mercury is a common name. Just like lead is Pb. Why is it Pb? Because it's plumber Pb. Okay, so mercury, why is it Hg? Anyone knows the scientific name?
Some of them, but not all.
Okay, it's okay. Just this is not going to come up in exam, just to let you know additional knowledge so that you know. It's hydrogerium. Okay, mercury, the scientific name of element, hydrogerium. Okay. All right, so back to here. Okay, let's do a bit of conversion so that you know, okay, how to convert from one unit to another. I have a gas, okay, with this pressure, 797.7 millimeter hydrogerium. What is the pressure in pascals and in atmosphere? Okay, so take note, the question, I have two questions in one question. So always double confirm, what do they want? Highlight it. Okay, what is the unit in pascals and atmosphere? Okay, from the table just now, we know that 1 atm is 760 millimeter hydrogerium. Millimeter mercury. So if you have 797.7, okay, so what is it? Okay, no more showing all the steps by steps. Okay, I've been showing enough. Okay, if you want to find what is this, you cross multiply, things like that. Okay, it's a basic mathematics. So I hope even those who join in late, you watch back the lecture and understand this. Okay, so may I know how many ATM do you get? Okay, 1.05 ATM. Okay, so you solve one. What is the pressure in atmosphere? Okay, and then next, also from the table, okay, we know that 1 atm is 1.01 times 10 to the power 5 Pascal. Okay, because they want the unit in Pascal, so don't use kilopascal, use Pascal. So if I have 1.05 atm, okay, so what do you get? Okay, so it's actually, if you see this, like this Pascal. So of course, okay, one step further to those of you who are able to do it. From your calculator, if you type in exactly, you'll get this. But those who are able to do it, please do it in scientific notation. So 1, 2, 3, 4, 5. You move 5 times, so it will be 1.06 times 10 to the power of 5 Pascal. Okay, so this is called scientific notation. Okay, you move the decimal point until there's only one number, okay, in front of the decimal point. Yes. Yeah, if you want, you can. Yeah, you can use, okay? But it will be extra work because I'm going to give the unit in ATM and Pascal. If you want to convert it into bar, yeah, up to you, but it's an extra step for you. Okay, so yeah. Okay, so moving on, okay, to the laws. I would like to use the whiteboard. Okay. All right, let me simplify, okay, the laws that we have here in the whiteboard. Okay, give me the 4 factors that affects the gases. Pressure, volume, temperature, okay, number of mole. Okay, so Avogadro's law, okay, we have talked about Avogadro's law. Refresh, what is it about? Volume, directly proportional to number of mole, okay? So if the volume increase, number of mole also increase. So if I were to write this in an equation, I can write it as V1 over N1 equals to V2 over N2. Okay, so I hope you're familiar with this. Okay, it's something like if you get M1 V1 equals to M2 V2. Okay, just because the constant is the same, number of mole is the same. Okay, the same concept. What is 1 and what is 2? Okay, so normally 1 will be before the change. 2 will be after the change. Okay, we will look at the examples later in the calculation. Okay, so I did taught you in the previous class that if let's say I'm talking about the relationship of volume and number of moles, so pressure and temperature is constant. Okay, the other two parameters is constant. Okay, let's look at Boyle's law. Boyle's law talks about the relationship between pressure and volume. Okay, and I will write it this way. What does it mean? Inversely proportional. Okay, and inversely means opposite. Inversely proportional means if my pressure increase, my volume decrease. No longer directly increase. Okay, so this one is increase, decrease. Okay, so try. If I want to write this in the form of an equation like this, it will be P1 V1 equals to P2 V2. Okay, how do you form this? Okay, it's like if you want to write an equation, you will have to bring the number of mole down. If you want to write this equation, you will have to cross multiply. Okay, so you get P1 V1, P2 V2. Okay, meanwhile, Charles' law talks about the relationship between, the relationship between volume and temperature. Okay, and it's also directly proportional. So if you were to write an equation, can somebody teach me based on what I've written here? V1, T1 equals to V2, T2. Okay. To complete this table, okay, remember, if I talk about volume and number of mole, what is it? Must be constant. Yes, pressure and temperature constant. Okay, if I talk about pressure and volume, so the one that is constant is my temperature and number of mole constant. Constant means cannot change, okay? Before, the temperature and number of mole must be the same. After, the temperature and number of mole must be the same. Okay, that's what it means by constant. And Charles' law, I talk about volume and temperature. So the one that's constant is my pressure and number of mole. Okay, give you guys 1 minute. Okay, if of course I'll be very happy if you can do your own table like this. Okay, studying is like doing mind map, doing tables, simplifying. Okay. All right, let's just go through the slides, okay, even though I've simplified in the whiteboard. So Boyle's law, we talk about volume and pressure. So when I talk about volume and pressure, my temperature and number of mole. Amount of gas is always number of mole. My temperature and number of mole is constant. So I can come up with P1 V1 equals to P2 V2. Okay, so by looking at this example, okay, temperature constant, 300 Kelvin. My volume at 4, okay, I'm going to put in, okay, I'm going to decrease the volume becomes 2. Okay, so the volume decreases. So what happened to my pressure? Pressure from 1, it becomes 2. Okay, so the pressure increased. When volume decrease, okay, when I want to decrease the volume, definitely I must exert pressure. Okay, so when volume decrease, pressure increase. Okay, another real life example that's happening around us, okay, it's actually when you're breathing. Okay, when you're breathing, you breathe in oxygen. So when you breathe in oxygen, your lung has a high volume. When it has a high volume, you need to have a low pressure so that you don't push your oxygen out first. Okay, you have to process the oxygen, spread it around your body. Okay, and then meanwhile, when, okay, you want to exhale, okay, when you want to move out carbon dioxide, you want to exhale carbon dioxide, your pressure must be high so that it will push. When the pressure is high, it will push the carbon dioxide out so the volume will decrease. The volume of your lung will decrease. Okay? Okay, and then next we have Charles' law. Charles' law talks about volume and temperatures. So when I talk about volume and temperature, my pressure and number of mole is fixed, constant. So this is my equation, V1 T1 equals to V2 T2. Okay, so if let's say I have a glass bottle, okay, I trap some gases inside, I heat it, okay, in a double boil, okay, in a beaker of water, then the gas is going to expand and push the balloon. The volume expand, volume increase when the temperature increase. Okay. Okay, real life application, okay, where you can see this, okay, I believe some of you have played this before. Hot air balloon, or you know the lantern, whereby you have to burn the candle, okay, it's like very romantic, you write wishes there. So when you burn the candle, okay, the temperature increases. When the temperature increase, the volume increase. So it pushes, okay, the balloon go up because the volume increase. All right. Okay, if I combine Boyle's law and Charles' law, because Boyle's law talks about PV, Charles' law talks about V over T. When I combine them together, I have a combined gas law, so PVT. Okay, what is this and under what situation should you use which formula? Okay, it depends. If let's say in your question, they give you pressure and volume. And then they tell you the temperature and number of mole are constant. So you use Boyle's law. If the question gives you pressure, volume, and temperature are changing, then you use combined gas law. Okay, so we are going to do a few questions later. Okay, and then to recap, Avogadro's law talk about volume directly proportional to number of mole. So we have mentioned this. If I have the same volume of any gases at the same temperature and pressure, they will have the same number of mole. So if I have same number of mole, I'll have the same number of molecules, same number of particles. Okay, so of course, 1 mole, if I have 1 mole, we have learned this in the beginning of chapter 1. 1 mole of any gas will contain 6.02 times 10 to the power of 23 particles. Okay, so this volume of 1 mole of gas, we call it molar gas volume. So volume, when we look at molar, molar is always related to number of mole. So this phrase here, molar gas volume, talks about the volume in 1 mole. It's just that. Okay, and then standard temperature and pressure, STP, we have recapped earlier. Standard 0 degrees Celsius. In 0 degrees Celsius, 1 atm. 1 atm is 101.3 kilopascal. Okay, it's the same, huh? Just that different unit. Okay, so at this condition, 1 mole of any gases will occupy 22.4 decimeter cube. So you will see this value in your data booklet, page 5, okay, the important values, 22.4 decimeter cube per mole. And per mole means 1 mole equals to 22.4 decimeter cube. And RTP, okay, 25 degrees Celsius. In 25 degrees Celsius, 1 atm. Okay, 24 decimeter cube per mole. Okay, so if I combine everything, okay, Avogadro, Boyle's, ABC, okay, Avogadro, Boyle's, and Charles' law, I will get ideal gas law. Okay, ideal. How many of you have seen this ideal gas law before? Okay, you guys not encountering this? Okay, so PV equals to nRT. Okay, so P is the pressure, V is the volume. So this is Boyle's law, P and V. Okay, and then next, let me use another color. I have V and N directly proportional. So this is Avogadro's law. And next, I have V and T directly proportional. So this is Charles' law. I combine Avogadro, Boyle's, and Charles' law. I get PV equals to nRT. Pressure, volume equals to number of mole, temperature. Okay, what is this special R here? R is a constant value. Constant value means it's a value that you plug in. Constant, the same value. So this value, you can either choose 8.314 or 0.0821. Both are in your data booklet. What's the difference, okay? Personally, for me, I always use 8.314. So when I use 8.314, I keep on using, so I remember the values, okay? When I use 8.314, my pressure must be in kilopascal. Volume, liter or decimeter cube, because they are the same. Temperature for gas laws. Any questions about gas laws, about gases, temperature must be in Kelvin. Okay, and then the difference with this 0.0821 is the pressure is in ATM, atmosphere instead. Okay, but the volume is same, decimeter cube, and the temperature is still Kelvin. All right. Okay, and then there's a summary of formula here: Avogadro, Boyle's, and Charles' law, and ideal gas law. Okay, give you guys 1 minute to digest this, okay, while I open the simulation for you guys to see. Okay, so I have a very quick and simple, okay, simulation for you guys to see. Okay, I have gas particles in a container. Okay, so let me stop the time. Okay, when I stop the time, the pressure now is 5.6. Okay, sorry, I'm not sure if you can see. It's here. Huh? If you cannot, you look at your screen. Pressure here shows 5.6 atm. Okay, so if I increase the volume, what do you think happened to the pressure? Decrease. Okay, it's now 5.6. So let's see, 3.5. It becomes 3.5 atmosphere. And then, of course, the other way around, it's 3.5 atm now. If I decrease the volume, what happened to the pressure? Increase. 11.3, 11.6. Okay, and now very quickly, okay, so let's say, okay, I have this the same number of mole of molecules. I didn't add in new molecules. I didn't allow the molecules to escape. So I have the same number of mole of molecules. If I heat the container, you see it getting bigger. Okay, when temperature increase, volume increases. And when I put in ice, okay, temperature decrease, volume decreases. Okay, so just a very simple simulation. Okay, let's move on to Dalton, the D law. Okay, A, B, C, D. D law. D law is Dalton's law of partial pressure. Okay, we have pressure. Why we have partial pressure? Partial means part of the pressure. Okay, because this is normally for a mixture of gases. If I have a container, the container is a mixture of gases. Okay, I want to know this container, I have gas A and I have gas B. I want to know what is the pressure given by gas A. Okay, so I call it partial pressure of A. Because the pressure of A is not the whole pressure. Okay, so I call it partial pressure. Okay, when we talk about partial pressure, we have to keep in mind, number one, okay, the gases do not interact. Do not interact means they don't have any chemical reactions. They don't form bonds. Okay, so they don't interact. And number two, the gases act independently. Independently means they will give their own pressure. Okay, they don't care about any other gases around them. They will give their own pressure. Okay, so these are two things that you have to bear in mind. Okay, so pressure from any individual gas in a mixture, we call it partial pressure. For example, I have helium, nitrogen, and oxygen. I mix in one container. Okay, When I mix in one container, I would, number one, say that my helium, nitrogen, and oxygen, they don't react. Number two, they give their own pressure. Okay, so when helium is 1 atm, nitrogen is 1 atm, oxygen is 1 atm. Since they give their own pressure, so when I mix them in a container, the total pressure will be 1 plus 1 plus 1, each of these individually. So I will get 3 atm. Okay, so this is Dalton's law of partial pressure. Each gas gives their own pressure. So if I want the total pressure, I just add up all the gases. Okay, the pressure from all the gases. Okay, so this one again, okay, I have gas A, gas B, gas C. I mix them in a container. Gas A 100 kilopascal, gas B 250, gas C 200. When I mix them together, the total pressure will be the pressure of 100 plus 250 plus 200. So I will have a total pressure of 550. Okay. Okay, let's do a calculation, okay, to see how do we apply this. Of course, I will not just be giving you that gas A this pressure, gas B this pressure, gas C this pressure, calculate total pressure. Not that simple. Okay, so example of question 2. What is the partial pressure of carbon dioxide in a container? So in this container, I have 5 moles of carbon dioxide, 3 moles of nitrogen, and 1 mole of hydrogen. Total pressure 1.05 atm.
Divided by 9 and divided by 5.
Okay, very quick. Multiply by 5. Oh, okay. This is very quick, okay? But to those of you, if you get questions like this, you don't understand what to do or how to do. Okay, like I mentioned, it's a mixture. In this mixture, okay, around 5 parts, okay, is carbon dioxide. Okay, 5 moles, okay? And then I have 1 mole of nitrogen. And lastly, I have 3 moles of nitrogen. Okay, and I say that the total pressure is 1.05 atm. So how much is the partial pressure of carbon dioxide? What is the pressure of carbon dioxide? Okay, if you cannot remember, you cannot understand pressure, then we replace this with kilogram. I have a cake. Okay, carbon dioxide takes 5 parts. Nitrogen, 1 part. This one is the hydrogen. Okay, hydrogen, 1 part, and then nitrogen, 3 parts. How many kilogram is taken by carbon dioxide? Okay, isn't this way simpler for you? If you don't understand this, you replace it with a cake instead. Okay, then you have a pie. Okay, so carbon dioxide is 5 parts. If I want to calculate how much pressure is given by carbon dioxide, 5 parts divided by a total of 9, multiplied by the total pressure. Okay, how many kg of cake is eaten by carbon dioxide? 5/9 multiply 1.05 kilogram. Okay, so this one here, anyone can tell me, what do you call this? 5/9. This fraction, what do you call this? Ratio. Very good. It's the ratio. Okay, what is your part divided by the total part? We call it ratio. And because this ratio, we use number of moles, so we call it mole ratio or mole fraction. They are the same. Okay. All right. So what's the answer that you get? 0.583. That's all. ATM. Okay. All right. I have question 3. Perhaps you guys want to try. This is another way. Okay. So now I want you to calculate the mole fraction or the mole ratio the other way. Okay, if I tell you that neon partial pressure is 0.421 atm, helium partial pressure is 0.367 atm. Sorry, this is krypton. Helium is 214. Okay, and krypton is 0.367 atm. Okay, try to solve this and see. Well, just go have a spot check around. Yeah, should be if according to ideal gas law. Okay, how many of you managed to solve this on your own? How many of you figure out what to do? Just raise up your hand. I doesn't know. Okay. But you have an idea. Okay. How many of you have an idea what to do already? Okay. All right. So how do we calculate this? I have the partial pressure. So what do I find first? Okay. You have the partial pressure. You know that, okay, for example, this part is neon is 0.421. Oh, of course, neon is the largest part. Okay, 0.421. And then I have helium 0.214. And I have krypton 0.367. Okay, sometimes if you have no idea, you try to draw. Then when you draw, you get an idea. Okay, if the part occupied by neon is 0.421, how do you calculate the fraction, the ratio that is occupied by neon? Okay, so the mole fraction, okay, of neon, you use how much is occupied by neon divided by the all of them total. Okay, what's the total pressure? Sorry, 1.002. Okay. Do you need to multiply anything else? Percent? No. Okay, it's a fraction. I'm not asking about percentage, I'm just asking about fraction. So how many parts are occupied by neon? Okay. Subsequently, of course, mole fraction of helium 0.214 divided by the total, and then mole fraction of krypton 0.367 divided by 1.0. Okay, what do you get? 42 0.214, is it? Okay, and the last one 366. Okay, is there a unit? Why? It's a fraction. Okay, by right you have ATM and ATM cancels off. If you have this question in mind, what's the unit? Is there a unit? You just try to put in with the unit. Okay, then you know, oh, cancel off, so no unit. Okay. Okay, let's try question 4. Okay, question 4. Those who want to try, challenge yourself, you can try. Okay. So I'm just as usual. Okay, being me, I'll just draw something here. Okay, I have argon. It has a volume 90 centimeter cube and a pressure 5 atm. Temperature 25 degrees Celsius. It's mixed with nitrogen. Nitrogen N or N2? N2. Okay, gases, we have N2, except group 18. Okay, if you have any, you can refer. The periodic table is very, very useful. You must know how to use it. Okay, if you refer to your periodic table, everything in group 18 occurs as monoatom. The rest of the gases, okay, will be diatom. Okay, nitrogen, no information at all. Okay, so I'm going to mix them in a container. Mix. And this container has a volume of 200 centimeter cube. And the pressure, total pressure of the mixture is 4.5 atm. Okay, I'm going to teach you guys how to solve questions like this. Okay, first of all, you simplify. Okay, I always teach my students, first of all, you simplify the information. If you want to draw, you draw. Okay, draw a container. Okay. Okay. Secondly, okay, very important, ask yourself, are there any changes in the factor, the PV, number of mole and temperature? Are there any changes, or is the question just give you a bunch of information? Okay, this one, is there changes or is just a bunch of information? Changes, okay. Teacher, what's the difference, changes or a bunch of information? For me, it's a bunch of information. Okay, argon. I say that argon initial volume is this, initial pressure is this, initial temperature is this, and then I'm going to mix them. When I mix them, argon with the initial volume of 90 centimeter cube, it will now have 200 centimeter cube. So there is a change in volume. So it refers to changes. Okay, if there is a changes, if there are changes, okay, then you decide. The information that they give you, is it referring to Boyle's law or Charles' law? If it refers to Boyle's law, okay, let me use a darker color. The changes, okay, whether it refers to Boyle's law or Charles' law. If it refers to Boyle's law, you will have the pressure and volume. If it refers to Charles' law, you will have the volume and temperature. So these changes involve Boyle's or Charles? Boyle's, because they give you pressure, they give you volume, they ask you to find what are the partial pressure of argon and nitrogen. Okay, so it's the changes. Okay, then you know you are going to use Boyle's law. Okay, so what's the formula for Boyle's law? This will be number 3.
P1,
Okay.
equal to P2, V2.
Yes, P1, V1 equals to P2, V2. Remember at the beginning, I say 1 is before the change, 2 is after the change. Okay, what's the pressure before the change? 5 atm. What's the volume before the change? 90 centimeter cube. Okay, what's the pressure after the change? Is it 4.5? Is the pressure 4.5 after the change? No, why not? What is 4.5? Yes, 4.5 is the total. It is the pressure of argon plus pressure of nitrogen. This question here, I'm calculating for argon. So I need to find the new pressure of argon in this container. When my argon moved from 90 centimeter cube to 200 centimeter cube container, what is the partial pressure of argon? So this is P2. Okay, what's the new volume for my argon? 200. Okay, I have a next question for you. My volume in centimeter cube, do I need to change it to decimeter cube? Why not? As long as they are the same, okay? I have an equal sign here. As long as it's centimeter cube on the left, centimeter cube on the right, they can cancel off, then it's okay. Just make sure the units are the same left and right. Okay, don't need to purposely convert. Okay, so what is the new pressure of argon? 2.25. Okay, I don't have any information about nitrogen. So argon is 2.25. How do I find the pressure of nitrogen? Okay, we know the total is 4.5. We know argon is 2.25. Okay, we know the total is argon plus nitrogen. So 4.5 equals to 2.25 plus nitrogen. So nitrogen is 2.25 atmosphere. Okay. All right, I just want to share a very short story with all of you regarding this question, okay? A few semesters ago, I have a student, okay, who maybe, okay, she couldn't catch up during the lecture. So it's during the final exam. So you know, final exam is like 12 weeks after I have taught this. Okay, so 12 weeks later, she showed me this question in Microsoft Teams, and then she don't know how to do the working. So she asked me, teacher, this question, is it correct if I do it this way? I have the total pressure is 4.5. Okay, I have two types of gases. I have argon and nitrogen. So I divided by 2 and I get 2.25. Okay, because I give the answer here, 2.25, 2.25. So she asked me, teacher, this is my working. Is it like this? So teachers, is this correct?
No, just in this question, it's the same if we're doing the two.
Yes, so it's called incidentally, so called incident. So okay, this question is divided by 2, you get the answer. Okay, why am I sharing this story to you? Okay, I want you to understand why tutorials I don't share the answers. Because this is what happened. When I share the answer, you have only the question and the answer. So you use the information in the question and you try to create a working to get the answer. Okay, so that was what happened to my student. Okay, she got the information, she got the answer, so she figured out, oh, is this the way? Okay, so no, it's not. Okay, all right. I think one more slide. Okay, just discuss this, then I'll let you off for a short break. Okay, all right. I have a flask. Okay, and then this flask is equipped with a valve. A valve means a tap that I can open and close to allow gases to go in and out. Okay, in this flask, I have 3 mole of hydrogen gas. And then I'm going to open the flask and I'm going to introduce 3 mole of argon gas into the flask. Okay, the first question, what happened to the pressure of only hydrogen gas in the flask after I introduce argon? Okay, I have hydrogen originally in the flask, and then I open the valve, I introduce argon. What happened to the pressure of hydrogen? Will it increase? Will it decrease? Will it remain the same? Okay, how many of you say the pressure of hydrogen will increase? Put up your hand. Okay, don't worry. Okay, how many of you say the pressure of hydrogen will decrease? How many of you say the pressure remains the same? Okay, the answer is remain the same. Can you guys explain why remain the same? Okay, because we learned that in a mixture of gases, if the gases, they mix together in a container. Okay, so number 1, they don't interact. And number 2, what I mentioned just now, they give their own pressure. Okay, so whatever pressure that hydrogen is giving in the container, when I introduce argon, hydrogen is like, don't care. I'm just going to give my own pressure. I don't care what happened. Okay, so it's individually giving pressure individually. So the pressure of hydrogen remains. Okay, B. How do the pressure of argon and hydrogen compare? Okay, that means compare the pressure of argon and the pressure of hydrogen. Is it argon higher than hydrogen, or argon lower than hydrogen, or they are the same? So this time louder. Okay, how many will say argon is higher? How many say argon is lower? How many say they are the same? Why the same?
They have the same number of moles, and no matter which gas you use, they always have the same.
Okay, because we learned just now, if I want to calculate the partial pressure of argon, let's say, how do you calculate according to this? Mole fraction. So how do you get the mole fraction? Okay, so total mole, okay, mole fraction. If I want to calculate pressure of argon, the total number of mole is 6. Then the number of mole of argon is 3. They will give the same mole fraction. Okay, so since they give the same mole fraction, so the total pressure is also the same. Okay, as long as they have the same number of mole, they will give the same pressure. Okay, and lastly, Draw a relationship between total pressure and the pressure of the two gases. A relationship, equation to show the total pressure and the pressure of the two gases. How do you relate that? Okay, total pressure is pressure of argon plus pressure of hydrogen. Okay, if I want to simplify this further, can I? This is correct, but I want to simplify this part. Anyone? P1 plus P2, okay. Anything else? Simplify it further. Yes? Times 2. Okay, very good. Why? Because argon, let's say, is the same pressure. We learned from B is the same pressure. Let's say the pressure is X. This pressure will also be X. So it will be 2X. Okay, so you can say it's 2 times the pressure of argon, or you can write it as 2 times the pressure of hydrogen. Okay, all right, give you guys a break. It's 9:51, so we will meet at 10:01. Okay, I'm going to pass the attendance around. Okay, I'm going to use a new attendance sheet because the previous one is very messy. Okay, so try to find your name. If you are new and your name is not in the list, please go to behind. Okay, and write your name behind. So I have to tick. Okay, I have to mark with a tick because I cannot imitate your signature. But when you get the paper, please sign as usual. Don't tick. Okay, sign as usual. Right? 2, 1. Go on. 2.
1.
Не повезло. Я
Просто галочку ставить.
Не, вот ребята. Могла задать.
Or they share the same.
Yes, they share the same volume. But the volume will not be divided. Like it will not say that because I have 200 centimeter cube, then I have two gases. So each of the gas is 100 centimeter cube.
Like this question, I think. So initially, if say this in this class we have constant volume, and then hydrogen gas occupy it.
Yes.
But then when another gas is introduced, in it, like the gas will occupy some volume, and then will
They occupy the same volume because, okay, the total volume of this class is the same. Okay, initially maybe I have only hydrogen. So when I have only hydrogen, let's say the hydrogen will give the pressure 1 atm because only hydrogen. Okay, and then when I have argon added inside, the argon will occupy the same volume. I cannot restrict that. Oh, hydrogen occupy this part, argon occupy this part. Cannot, because they are going to move around and they will occupy the same volume.
But then why the pressure will not increase?
It will increase, but the pressure increase is because, let's say my hydrogen is 1 atm. Initially, if I only have hydrogen, it's 1 atm. And then if I introduce argon, argon is also 1 atm. Then the pressure becomes total pressure. It will be 2 atm.
So the pressure that increases total pressure.
Yes,
Okay.
because I add on, so total pressure. And logically, okay, when I have more molecules inside, at first I only have hydrogen, so it's only 1 atm. When I have more molecules inside, more banging on the wall of the container, so more pressure is created.
Because I think that if like there is two gases in a container, and one of the gases, like the frequency of collision will increase, right?
That is why we say okay, when we talk about all these gas laws, we have to assume that they are not interacting. So when they are not interacting, that means they are behaving, because actually we are talking, when we talk about these theories of all the gases, of all the laws, we are assuming that all the gases are perfect gases, ideal gases. So ideal gases, they don't interact with one another, they don't create bond, and because of their rapid movement, let's say if they created a bond, it's going to break. So even if there's any interaction, it's going to break. So that's why at the beginning, we assume that they don't interact and they will just exert their own pressure.
Okay. Thank you.
But of course, in reality, we know that definitely there's a bit of difference. Yes.
Like, can we took this as total
Okay.
pressure of two gases,
Okay.
and here all.
Initially, can I draw?
Yeah.
Okay. Initially, I have argon. Sorry, let me look at the question. Okay, argon and nitrogen. Okay, initially I have argon. So argon will occupy, this one is 90 centimeter cube, and the pressure that they give is 5 atm. Okay, and then I'm going to mix them into a larger container. So this container is 200 centimeter cube, and the total pressure is 4.5 atm. But this container contains argon plus nitrogen mixture. Okay. All right. So your question is why you cannot assume that argon is 4.5. All right.
Now I want to find the total pressure here in the first.
Okay. Okay. This is the pressure of only argon. If I have only argon,
Yeah, I know, but we know the volume first and the volume at the end,
yeah, this is the
and we know the
pressure.
pressure, so we can find the first pressure, total first pressure.
No, there's no total first pressure. Okay, what we are doing
No,
here?
you can find it.
No, it's already coming here.
No, I mean the sum of argon and hydrogen.
Okay, how do you find it?
I mean, we can find B1, it will be this.
Okay, then we'll continue. So how do you find it?
Then we have that it is
How do you get 70? Can you replace the values maybe? Oh,
then we get 10.
cannot. Because this one is 200. This one is 50. So you cannot. Okay, what you are doing here is, you are doing P1 V1 equals to P2 V2. All right, and then that's why you put the V here. And you're assuming that this pressure is 4.5 atm. All right.
Alright,
Okay.
because I
Yeah.
take two bit.
Yeah, that was why I say you cannot assume it's 4.5 because this 4.5 is a mixture of two gases.
Yeah, but
Okay.
I mean that it's mixture
it's a
of gases.
mixture.
And this also, I mean that's mixture of two gases. I want to take it.
No. You already have the mixture, the pressure for the mixture of two gases. You don't need to calculate it anymore. Because here you haven't mixed, it's individual gases. You will mix in a container. So we use this formula correct. P1 V1 equals to P2 V2. But this is I have to calculate individually. Because okay. This one argon. What we are checking is argon at this volume. Initially, I have this volume. So at this volume, I will have this pressure. So when my argon, I shift to a new volume, the volume increase. So when the volume increase, I need to find the new pressure of argon because the pressure will decrease. boils off. Okay, the volume will increase. So I'm assuming that argon in the new container will no longer be 5 atm because the pressure is going to decrease. So that's why I find P2 is the new pressure of argon. Only argon, because I have to calculate them individually. Here, in this 90 centimeter cube, they haven't mixed. So you cannot say that this pressure is a mixture. Because this volume, 90 centimeter cube, is a volume for only argon.
Nitrogen doesn't have a more here.
Yeah, that's it. Yes, correct. So you cannot add inside.
Isn't it the same too?
No. Because it wasn't in the question, it wasn't stated in the question anything about nitrogen. So that is why you have to find argon first, and then from the value of
Oh,
argon.
it was mixed after.
Yes, after.
Oh,
Yes,
I see.
that's one.
And the second.
Yeah, so it's not individual. Okay.
About the next question.
Oh.
What we should write as the answer, or we just write like this?
Oh, just say how do the pressure compare? The pressure is the same. The pressure are
Or just write like AR, argon same with hydrogen.
like this pressure of argon same with pressure of hydrogen. Then if you need to explain, you can say because the mole ratio is the same. Because we use mole ratio. Remember mole ratio? We use mole ratio multiplied total pressure. So because their mole ratio is the same, so they will have the same pressure.
Also, we just write like two equation.
Yeah, and then you explain.
Question C also same.
Yeah, for question C, you just write like this because the relationship is like this, like this. So just like this.
Teacher, these values are given in our
In the data booklet. 101 kilopascal. So you just use more. All right, class, get ready. We are going to start soon. Yes. Testing. Hello. All right, class, can we continue? Okay. All right. So if I have somebody, please mute your speaker. Speaker, not my mic. Okay. All right. Okay, now I have a container. If you notice, this container is empty without gas molecules. So when it's without gas molecules, my pressure is 0 atm. Okay, so my question is, what causes pressure? Why is there a pressure? Why in this condition I don't have pressure? Yes, okay, it's when gas particle hitting the wall of the container. For example, if I release one molecule inside, before the molecule hits the wall, it's still 0. Right after the molecule hits the wall, you start to produce pressure. Okay, so that's how pressure happens. Okay, so let's say I pump in some gaseous molecule. Oh, before that, okay. Okay, we're moving into something called kinetic molecular theory. So kinetic molecular theory, we are going to investigate, okay, the movement of the gas molecules. Okay, so the kinetic of the molecule. Okay, let's say I have one gas particle for you to compare, okay, this gas particle and the volume. Definitely you know, right, okay, if you have a gas molecule or a gas atom, it will be very small, you cannot see it. Okay, what can you say regarding the size of the molecule, the size of the gas molecule, the size of one gas molecule when you compare to the volume? Is the size significant or not significant? Is the size of the molecule significant compared to the volume, or is it not significant? Not significant, because the size of the particle is very small. Remember, I showed you in the lecture, okay? I zoom in, carbon atom is so small, you cannot even see. Okay, this one, of course, you can still see. Okay, but the real one is even smaller. Okay, so the first thing is the size of the gas. Okay, the size of the molecule is not significant compared to the volume, or the volume is very, very big compared to the size. Okay, okay, next I pump in molecules. Okay, what can you say about the movement of the gas particles? Do they stop anywhere, any point of the movement? No. Okay, they didn't stop, so we say that they are constantly moving. Okay, do they have a single direction, like I must move left, I must move right, or it's random? It's a random motion. Okay, so we say constantly moving, random direction. Okay, next, do you see them hitting one another? Hitting the wall of the container? Okay, after hitting, do they stop or they still continue moving? They still continue. So we say that collisions, when they collide, when they bump into each other, it's elastic. Elastic means they bang onto the wall and they come back. Okay, you know how you throw those rubber balls? Okay, elastic collision. Okay, and lastly, let's say I have a mixture of gases. Do you see them forming any bonds? No. Okay, so the fourth one is we say they don't interact, they don't have forces of attraction. Remember Dalton's law of partial pressure just now? We talked about two things. What are the two things? One, they don't interact, they don't cause a reaction. Number two, they give their own pressure. Okay, so when we talk about gas laws, we talk about kinetic molecular theory, we assume the gases are perfect. Perfect means they fulfill the four things that we mentioned just now. Okay, what are the four things? Let's go back to the slide. Okay, the four things are number one. Okay, the gas have negligible size. If you cannot use the word negligible, you can say that the size is very small, or you can use the word just now, the size is not significant. Okay, compared with the volume. Okay, I'm trying to simplify the words for you because I understand some words are not commonly used. Okay, so you can understand this with your own words instead. Okay, so the first thing is the size, very small, not significant. Volume is very big. Okay, number two, particles don't have, okay, you cannot use the word negligible. You can say do not have intermolecular forces of attraction. Why? Because you see they're constantly moving. So let's say, okay, when you move, even when there is a slight interaction, they are about to form a bond, they will have moved, and then the bond is broken. Okay, so they do not have intermolecular forces of attraction. Number three, the gas molecules, we are talking about movement of gas molecules, okay? The gas molecules constantly keep on moving and it's in a random direction. Okay, so whether you use the phrase constant random motion or you say constantly moving in random direction also can. Okay, and lastly, if there's any collisions between the molecules or with the wall of the container, they are elastic. Elastic means you bang on it, it comes back to you like a rubber. Okay, elastic. Okay. I would like to move to the whiteboard again. Okay. So gases, okay, we have two types of gases. One we call ideal gas. Ideal gas, ideal means perfect. Okay, 100% perfect gases. And what does ideal gas mean? Ideal gas means if the gases fulfills the four criteria of our kinetic molecular theory just now. Okay, fulfills all the four. Okay. Another one is real gas. What is real gas? Okay, we know something called expectation versus reality. Ideal gas are the expectation. We expect the gases to behave ideally, perfectly, in constant random motion, no intermolecular force of attraction and things like that. But in reality, maybe the gases are not so perfect. Okay, so these are the gases in reality. So maybe they do not fulfill our kinetic molecular theory a little bit. Okay, not directly not fulfilling, but maybe some of the points it didn't fulfill. Okay, so now we're going to investigate under what condition or what situation ideal gas will become real gas, and under what situation my real gas can behave more like an ideal gas. Okay, so I've explained what is ideal, what is real. Okay, the conditions that are going to change them is divided into pressure and temperature. Okay, so let's say pressure. Okay, do you want to discuss about high pressure or low pressure? Choose one. High pressure, okay. All right, what happens when pressure is high? Boyle's law. Boyle's law. What happens if your pressure is high? Volume is low. What happens when the volume is low? Relate to the four kinetic molecular theory. If your volume is low, what happens to the size? Okay, the volume. Just now we talked about volume is very, very big compared to the size. If your pressure is very high, you squeeze the volume until very, very small. So what happens to the size of your particle? Size of particle become significant. You cannot ignore anymore. Okay, I give you something to imagine. Okay, let's say you have this big size, and then this is the size of a particle. Okay, at a high pressure, maybe your volume become like this, and the size of your particle didn't change. So at this time, when your volume is small, the size of the particle becomes significant. Does this fulfill kinetic molecular theory? No. So is this ideal gas or real gas? Real gas. Okay, so we put it here. Number one, high pressure, volume is low. When volume is low, size of the particles become significant. Okay, so high pressure is where your ideal gas will behave more like a real gas. Okay, where your ideal gases will move towards real gases. Okay, if high pressure causes your ideal gas to become real gas, so in what pressure will the real gas become ideal gas? The opposite. It will definitely be the opposite. Okay, so what happens if low pressure? Volume is high. So what happens if the volume is high?
The size of the particles doesn't matter.
Doesn't matter. Yes, the size of the particles is no longer significant. Okay, I like the word doesn't matter. Okay, yes, acceptable. I want you to express yourself. Okay, don't purposely memorize the words that I use. If you understand it, you explain it with your words. Okay, next, temperature. Do you want to discuss high temperature or low temperature? Choose one.
High.
High, okay. So what happens when you have high temperature? Kinetic molecular theory. So if high temperature, what happens to the kinetic? More kinetic energy or low kinetic energy? Okay, higher kinetic energy. So your gas particles, when high temperature, they will have more energy. What happens if they have more energy? We talked about one. Okay, yes, very good. More collisions. Okay, so more collisions, and the collisions will become elastic collisions. Because they move so fast, they collide and bounce back, collide and bounce back. Okay, more collisions, and they will be elastic collisions. Okay, what else? We talked about collision, elastic collision. We talked about size of the particle under pressure. What are the other two? Okay, talked about volume and the size. What are the other two? Force, okay, force of attraction. Okay, what happens to the force of attraction if you have high kinetic energy? Okay, whenever you want to form a bond, because the kinetic energy is so high, they move so fast. Whenever you just want to form a bond, broken. Form a bond, broken. Okay, So all the forces of attraction, sorry, I use short form, forces of attraction, FOA, will be broken quickly. So there will be no forces of attraction. What's the last kinetic molecular theory? Constant random motion, size is not significant, forces of attraction not significant. The other one? Elastic collision. Yeah, we talked about elastic collision. Right out. What's the other one? Oh, constant random motion. Okay, we combine already, constant random motion and elastic collision. Okay, then, okay, since no force of attraction, okay, higher collision and those collisions are elastic collision. Does this fulfill kinetic molecular theory or away from kinetic molecular theory? Fulfill. So when fulfill, it means that I'm moving to this arrow towards ideal gas. Okay, so let's plug in our explanation here. Temperature increase, kinetic energy increase. When kinetic energy increase, more collisions, and the collisions are elastic collision. And then there is no forces of attraction because they will all be broken. Okay, all right, if towards ideal gas, we have high temperature. So if I want to move away from ideal gas, temperature must be low, opposite. Okay, then you can build your own explanation. Temperature low, kinetic energy low. Okay, so there will be lesser collisions because the particles move slower, no more constant random motion, okay, lesser. And then there might be, okay, I'm not saying there will, okay, there might be temporary force of attraction, more significant, okay, it cannot be broken because not enough, maybe, okay, not enough energy to break it. Okay, give you guys a few seconds, 30 seconds, I think, to digest this, then we move on. Okay, I hope you guys understand. I moved to the whiteboard so that we can generate based on our own understanding. Of course, okay, they are all, the information are all in the slides as well. Okay, real gas becomes ideal gas when the pressure is low because the volume is very big. Okay, and then real gas become ideal gas when my temperature is high because I can break the force of attraction. Okay, and then deviates. Deviates means move far from. Okay, so real gas becomes far away from ideal gas. So it becomes more like a real gas when it has high pressure, because high pressure size of the gas cannot be negligible, cannot. Okay, and then a low temperature, force of attraction becomes significant, cannot ignore anymore. Okay, but we have already put this in the whiteboard just now. Okay, let's try to calculate this one. Okay, remember the methods. Any questions regarding gas law? The first thing, I list down the information that I have. I want to calculate volume. I have number of mole, 0.5 mole, carbon dioxide, pressure 150 kilopascal, temperature 19 degrees Celsius. First step, I simplify information. Second step, determine whether there are changes or it's just a bunch of information. So which is this? Information. Very good. If it is a bunch of information, just now we talked about changes. If it is changes, whether it is boys or Charles. When it is just a bunch of information, definitely ideal gas equation. PV equals to nRT. Okay, so just to illustrate to you, pressure, because my R, remember I mentioned earlier in this class, R, I will always use 8.314. So my pressure, I will use pressure in kilopascal. My volume, this will be in decimeter cube. My number of mole, 0.5. Okay, what about temperature? Must be Kelvin. Okay, any questions regardless what method you use, temperature must be in Kelvin. So how do you convert degrees Celsius to Kelvin? At 273. Okay. All right, so what's the volume? .09 decimeter cube. Correct? Okay, but of course, if you use 0.0821, then it will be slightly different. Okay, so I've shown you two different questions and two different ways of solving it. One of it involves changes, so identify whether it's boys or girls. Another involves information. Okay, so can I give you questions 6, 7, 8, 9, and 10 as homework? Okay, because I still need to discuss with you about your assignment, so I need some extra time. Okay, so I give you as homework. I give you guys 1 day to try to do it. Those who are stuck, I will upload a video to guide, not to show step-by-step working, just to guide you according to the same thing. Okay, I'll upload the video in your recording. If you are stuck, you can refer to that. But of course, if you are able to do it on your own, that will be the best. Okay, 6, 7, 8, 9, 10. Okay, solve it on your own, try it on your own. Okay, I'll go to the last part, okay, of this chapter. It is ideal gas law equation, okay, the application. Because we know PV equals to nRT, okay, and we know that N is mass over molar mass, okay. So if I replace the number of mole with mass over molar mass, and I rearrange, okay, PV go to the bottom, molar mass comes on top. Then I rearrange the equation, I will get molar mass is mass R times T divided by P times V. And I know that mass over volume is also density, so I can replace this with density. Teacher, do I need to memorize this? Okay, if you don't want to memorize this, no problem, but you need to know PV equals to nRT, number of mole, you can replace with mass over molar mass. Okay, you can derive this on your own. Don't need to purposely memorize. Okay, but just to let you know, if you have the density, you can replace inside. Okay, all right, let's try this one example. I have a flask with this volume and this mass, this pressure, this temperature. Calculate relative molecular mass. Okay, again, as I said, you don't need to memorize the equation. You know PV is nRT, N is mass over molar mass. Okay, then you substitute the value. Again, my R will be 8.314. My personal preference, Okay, so my pressure in kilopascal, correct? Okay, double check your R and the units for your factors, okay, for your PV and T. Okay, volume is 2 decimeter cube, so correct. My 8.314, I will use kilopascal and decimeter cube. Then I have the mass. I need to find relative molecular mass. Temperature must be Kelvin, so 273 plus 20, 293. Okay, then I just rearrange, okay? So relative molecular mass. 32.155. Is it somebody? Okay. Is there a unit? Why? It's relative molecular mass. Okay. Anything relative, comparing, no unit. Okay. So double check with the answer, with the question. Okay. Question 11 and 12. Can you guys also try it? Okay. The same thing, try it. Okay. All right. I wish to move on to assignment. Okay, to explain to you what you need to do. Okay, you can go to chemistry 1 page, go to files as usual. Okay, under files, you have something called title selection, FIS1, FIS2. Okay, I'm going to explain to you what, wow, so fast. Correct, right? Your FIS1 and 2. Oh, some people have been filling up when I was teaching. Okay, so now I know who is filling up when I was teaching. Making bricks from waste. I think Samrat is taking the.
I wrote to you.
So is this your group? Okay. For your information, okay, Samrat has booked the. He made the effort to come and see me and say he wanted the title. Okay, so it has been taken by him. So this group, please change, huh? Okay, so I would like to explain, okay, so you can open this highlighted peach. Will be the group leader's name, okay. Topic that you have chosen will be on top here, okay. If I put a green color, that means you have booked the title, so you can take this title. Okay, so the one that fill in after that, please check the green color, make sure. Okay, it's none of the title that you've chosen. Let me check. Soft drinks. Okay, fruit juice can. pH temperature. Okay, okay. Okay, so you can fill this up. And please don't add numbers on your own. Okay, I have checked your class has 78 students, 8 groups with 6 members and 6 groups with 5 members. Teacher, I cannot find a group. If you cannot find a group, the least, the minimum that you can do, okay, maybe you just put your name. For example, okay, this group here, I have only 5 members. So there's 1 empty slot. You can just put in your name there. Okay, those who have full members, okay, please, you know you have 6 members, put your name in the 6th slot. If you have 5 members, put your name in the 5th slot. Teacher, I have 5 members, but all the 5 member slot has been taken. No choice. You have to go to the 6 member slot. Teacher, I have 6 members, but all the 6 member slot has been taken. No choice. You have to remove 1 member. Okay, so first come, first serve. Quickly put in your name. Okay, and as a last reminder, the last date, okay, for you to form a group, I believe last week I've already told you can start forming slowly, okay? So I hope you guys can have your groups by tomorrow. If you need extra time, you come to me, let me know personally. Okay, I do understand it's a short notice, so you can let me know personally. Okay, group contract will be tomorrow. And I've already reminded, must be printed, must be signed physically. Pass me the physical copy. Okay, any question, anything you want to ask about this?
Where is the file? And the template is right.
Under Microsoft Teams, go to Files, Title Selection, FIS1, FIS2. Yes. Okay, any questions? No. Okay, where's my attendance list? Is it being passed around? Who is holding the attendance list? Can you take up your hand? Okay.